okay, we pick it up at average value of a function. So normally, when we want to do an average of n numbers, we simply add up the numbers and divide by how many there is. So how can we use this to define the average value of a function that would have an infinite number of values? See, a regular function has values at every single x value, so we don't have these individual x values we can use. So consider the following approach. Break the interval a to b into a large number of little subintervals, the exact same way we were doing with Riemann sums. And just the exact same way that we were doing with Riemann sums is we would do, to define each of these intervals, as saying delta x equals b minus a over n, the exact same way. So we're making the same intervals we did with the Riemann sum. Just we haven't really said it's a rectangle per se. And then we take some number in that interval to represent the function in that section, to say, okay, we're going to use some representative value. And so what you get is to take the averages, we say, okay, find the function value at the first x value we select, which would be in the first subinterval. Then add to that the y value at the second x value, which would be in the second interval. And you just keep going like that. And you add up a bunch of y values chosen from each of these subintervals. And you divide by how many you did. So you're really averaging a bunch of values, but you're only selecting some of the values from the function. So what we end up with here is adding up, well, this is just from the previous slide, is we're adding up all of these different function values and dividing by how many there is. So now we see that the n is a common factor, like it's a 1 over n, like it's an n in the denominator. So we common factor that, and we go, okay, so now 1 over n, and then we're left with just adding up all of these function values. So we've common factored that piece out. Now, using the same notation we were using before, this adds up to, we can write it as a sigma notation going from k equals 1 to n of f at ck. And all we're saying is go use the sigma notation to add up all these different y values that we found in each section. And this is really starting to look like Riemann sums here. And really, we can go one more step and say, okay, so if we know that delta x is b minus a over n, we can sub in for 1 over n, and it becomes delta x over b minus a. That's we're just rearranging over here and saying, okay, well, delta x, move this b minus a over here, and we get b minus a. So then delta x over b minus a is the 1 over n, So what we get here is then the sum that we were working on. We now can replace that 1 over n with delta x over b minus a, and we still have this Riemann sum in here, k equals 1 to n of f at ck. And then notice that, here's the next line here. If I move that delta x back into the sum, sort of uncommon factoring it into here, what I get is 1 over b minus a, sigma k equals 1 to n, and oops. There, that's better. 1 over b minus a, k equals 1 to n of f at ck delta x. And all I've done is move that delta x inside the sigma, and then that becomes the Riemann sum. that piece right there is exactly the Riemann sums we've been doing. That is, pick a representative value out of each interval and multiply it by the delta x. And so that whole Riemann sum is just multiplied by 1 over b minus a. So when we're done and we say, okay, well, we want to go to an infinite number of these little rectangles so that we get as close to the answer as we can, we're left with the integral, basically, is that piece that I've underlined there is the integral. So if we want to find the average value, simply put, all we do is go 1 over b minus a times the integral from a to b of f at x dx, because that's what that piece is it's the integral, and we're just transferring that over the integral. So let me say it another way. If you want to find the average value of a function, you do the integral from a to b of f at x dx, but then divide it by how wide the interval is, because you got to take the area of this whole thing and divide it by the b minus a. So, to use that, okay, I'm going to do an example later of exactly how to use that to find average values. It's not too hard. If you can do integrals, finding the average values, not particularly difficult. But to actually use it to go after mean value, consider this function here. And again, the picture's similar to other pictures we've made. Some function that is defined on some interval a to b. Now, we know that the area under this curve, the net area, is integral from a to b of f at x dx. Now, what I want you to consider is, so there's the whole area there. Now, I want you to consider a rectangle whose base is b minus a and height given by some point on the curve. So we can choose any point in the curve and say, okay, here's some point, and then we don't have to imagine an exact point, or sorry, a specific point, but any point like that will get some rectangle. And the area of that rectangle would be f at c, so the height of that rectangle, multiplied by the width, which is b minus a. Okay, so you're unimpressed at this point about what's happening, but we're just setting up for something here. Now, if that c value that we use is actually the minimum of the function on that section, the area will be smaller than the area we're looking for. Again, you're unimpressed. You're saying, well, of course, if you use the minimum y value, of course, what you're going to get is a lower area than what we're looking for. Now, if we use the maximum, then the area of the rectangle will be larger. So if we use something like this, we get a larger area. Again, you're unimpressed. And this is the beauty of the mean value theorem. Each step along the way is sort of look at and go, well, yeah, of course. And then some giant conclusion comes out of the mean value theorem when you do things like that. Therefore, there must be some point on the curve higher than the minimum and lower than the maximum, such that the area of that rectangle is exactly right. So it's sort of like Goldilocks and the Three Bears. The rectangle, the smallest rectangle is too small, the biggest rectangle is too big. So in between there somewhere between the lowest and the highest is some exact c value where the area of this rectangle is exactly the right area of the curve. You might be like, well, that's fine. You're just saying that it's possible to find it. And yeah, this is really an existence theorem. It's saying there is some x value out there, and we're calling that x value c, where if we use that c and find the area of a rectangle, it will be exactly the area under this curve. So there is some rectangle out there that's exactly right. And it has to be true, because if we use the max, that's too high. If we use the min, that's too low. So if we go from the max and work our way down towards the min, at some point there's going to be something that exactly does the right area. So there must be some c, comma f at c, such that f at c times b minus a is equal to the integral. That's what the mean value theorem says. It must happen somewhere along the way. So there is an f at c. There is a value that is the average value. That's what we were just working on. There is some value between a and b that is exactly the average value of the function. That's what this next sentence says. The above result indicates at some point in the interval, we will find the average value of the function. And this idea is known as the mean value for definite integrals. It says, if f is continuous, then at some point we will find that the function takes on the average value all the way across that section. And it's a very interesting theorem because for a while it's like, what are you talking about? And then it becomes so obvious. It's like, oh, of course. There has to be somewhere. If a function goes up and down and has some average value in there, some point in there has to hit the exact average value when you're talking about a continuous function. So we got a little example to tie this all together. It says, with the aid of a calculator, find the average value of f at x equals 4 minus x squared on the interval 0 to 3. So we're going to have to do an integral here, but we're not quite up to doing integrals of something that's complicated yet. So we're going to have to use our calculator function with the integral function on there to be able to find this integral when we get there. So let me just show you how that's all going to go. So what they want is the average value of, so what was the function again? They wanted the function f at x equals 4 minus x squared. So first find the average value. Average of f. And we just found out that the average of the function will be 1 over b minus a times the integral from a to b of f at x dx. So in this case, it was from 0 to 3 that they wanted the average value from. So I got to go 1 over 3 minus 0. So I'm going from 0 to 3. And then my function, my integrand here, was 4 minus x squared. Now this integral is, for at least one more lesson, a little bit too hard for us to do. So we'll just use our calculator to do it for now. So when I type into my calculator and get to my integral function, my integrand is 4 minus x squared. And I type in 0 to 3, and I hope you're doing this on your calculator too to try it out to make sure you know how to do it. I get the answer, the simple answer, of 3. I've simplified that, and I've made that into a 3. So apparently the average value of this function, 4 minus x squared, its average is 1. That's the average value you're going to get. So average value of f. There we go. Now, the question said something more. It says, at what point on the interval does the function assume its average value? So the theorem says that at some point, this function here, 4 minus x squared, will take on the value 1. Somewhere along the way, it's got to happen. So I can do that math over here. I can say, okay, well, I want to know when 4 minus x squared will be equal to 1. I go negative x squared equals negative 3. I'll just move that 4 over, get rid of the negatives. X squared equals 3. And so then I get the answer x equals square root 3. And you're like, well, where's the plus minus? Well, we're between 0 and 3, right? This question, and I'll use a different highlighter here. This question said, oh, between 0 and 3. So if I'm between 0 and 3, I'm not looking for that negative value. I'm looking for the positive version of this. So did I answer the question? At what point on the interval does the function assume its average value? At x equals root 3, f at x takes on the average value of 1. And that's all there is to it.